Hi, this is a talk about the 2021 update on a 2020 preprint of Dorothée Frey and myself dealing with fixed-time LP estimates for certain wave equations. More generally speaking, this is part of the development of Hardy space methods for wave equations that has recently gained some momentum, starting with a joint paper of Andrew Hassel, Jan Rosendahl, and myself published in 2020. We're trying to get LP information, LP in space, on the solution of the wave equation, and what that tells us is that the solution of these equations can not be too concentrated on a small region of space. That is because the L2 norm is controlled, so if you also control the LP norm for large values of P, you cannot possibly be concentrated in a particularly small region of space. Now, when we have Strickhart's estimates, we get exactly this kind of information, but averaged over all time, whereas a fixed time estimate gives you this information for every value of your time parameter. And the question we're really trying to answer is, what are the data for which such a fixed time estimate can be proven?
Now, this is the result I want to discuss in this talk. We consider the group on L2 generated by the square root of an elliptic differential operator of order 2, something in divergence form or not. And then we prove that if you regularize that L2 bounded group enough, and enough is defined by this number, then what you get is a family of bounded linear operators on LP. Put in a different way, if you start your wave equation with the data in an appropriate fractional power space of the operator L, then your solution lands in LP for every value of the time parameter. Now, if L is just a standard Laplacian, then this result is a celebrated theorem due independently to Peral and Miyake in 1980, and what we are doing here is extend that result to operators with some Lipschitz regular coefficients. Now, what kind of operators? Well, we really need the operators to arise as square of Dirac operators. So the second order operator needs to be a square of an appropriate first order operator. Now, I really want to be able to treat divergence form second order differential operators, and those do not arise as square of first order differential operators acting on scalar valued functions. So the trick is to consider vector valued function, and then you can bring in a 2 by 2 matrix like this one, and the square of this 2 by 2 anti-diagonal matrix will be a diagonal matrix which entries are second order operators that can be either in divergence form or non-divergence form, depends which of this coefficient you choose to take equal to 1. Now that's our setup, and what sort of assumptions do we have on the coefficients aj? Well, we're going to assume that they are all Lipschitz continuous, that their derivatives are bounded, and that the coefficients themselves are bounded above and below. But very critically, we're going to have an algebraic assumption on the coefficients, namely the fact that all of the coefficients aj's are only functions of the j's coordinate of the variable x. And that is really to ensure that the group generated by the Dirac operator is a commutative group. Now, under these assumptions, we prove this generalization of Peral and Miyake result. But we actually prove a little bit more. What we do is we construct a space, which is a kind of Hardy space, and we prove that the wave group actually leaves that space invariant. And then afterwards, we prove embedding properties of that space compared to the Sobolev scale and deduce this result from the invariance of the group on an appropriate Hardy-Sobolev space. Now that actually has some advantages, and you can really see that if you look into the recent work of Andrew Hassel and Jan Rosendahl. The reason is, if you apply Peral and Miyake result, each time you apply it, well, you lose a certain number of derivatives. So if you apply it many times, you're going to lose many derivatives. But if you work on this space, you can apply the wave group on this space just as many times as you like, and you will only lose derivatives once at the very end once you compare the space to standard Sobolev spaces. And in the construction of parametrices, when you want to solve more complicated wave equations, this is particularly relevant.
Let me say a few words about the strengths and weaknesses of this theorem. The key strengths, of course, is that we are handling Lipschitz coefficients. If you think of Strickhart's estimates, they are known to hold for C11 coefficients, and there are counterexamples that tell you that they break down if you go below C11 regularity. So what we're doing here is going substantially below C11 regularity. Now, we're not the first ones to do that. For specific wave equations, specific coefficients, there are already impressive results going below C11, especially in the context of quasi-linear wave equations arising from general relativity. But we're trying here to be a little bit more general. Of course, that's the weakness. We're not treating fully general divergence form operator with Lipschitz coefficients because we have this algebraic requirement that the coefficients aj can only depend on the variable xj. That's really to guarantee that the transport group algebraically is a representation of RD. Now, this is frustrating, and this is something we want to overcome in the future by using more subtle functional calculi. But this was a good place to start. And I also want to point out that we have perturbation results. So we can add lower order terms to our operators, and at the level of these lower order terms, we do not pick up any algebraic restrictions. So we treat a fairly large class of operators, divergence form, non-divergence forms with lower order terms, and we have only an algebraic requirement on the main Lipschitz part of the operator.
So the heart of our analysis is what's called a wave packet decomposition. That's an idea that goes back to Cordoba and Pfefferman and consists in a refinement of the Littlewood-Paley decomposition. So you take your functions, you look at it on the frequency side and use Fourier multipliers to split it, first of all in Littlewood-Paley dyadic annuli, and then if you're in an annulus that has a radius roughly 2 to the j is a natural number, what you do is you split the annulus into further smaller pieces, and these pieces are such that their width is roughly 2 to the j over 2. So it's sometimes called a dyadic parabolic scaling because you have a parabolic relationship between the scaling in the direction of the wave packet and the orthogonal direction, and you use Fourier multiplier to essentially localize, we use smooth cutoff to one of these sub-regions of the Littlewood-Paley dyadic annulus. So the way we implement this wave packet decomposition is by using a wave packet transform. We use a family of Fourier multipliers that do some localization on the frequency space, and this localization has this anisotropy that it takes a preferred direction omega and scale in that direction like 1 upon sigma, but scales in the orthogonal directions like 1 upon square root of sigma. So this is localizing into these regions that I was drawing before. And you should think of the wave packet transform as a lift from L2 of the physical space RD into L2 of phase space, but you're decomposing the momentum variable into its direction, which is on the unit sphere, and 1 upon the size of momentum, which is the variable we call sigma here. And the key technical thing to remember about this decomposition is that if you're in a dyadic annulus roughly of radius 2 to the j with a very large j, then what's happening is that these regions are becoming very, very thin. The difference between the preferred direction omega and the direction of any eta inside that region is roughly 2 to the minus j over 2. So as you send j to infinity, you're essentially picking up one direction, and that's going to be critical to our analysis. It's going to make things look asymptotically one-dimensional. The way I like to think about it heuristically is that high momentum wave packets don't muck around. They pick a direction and they go there and only there pretty fast. Now, this wave packet transform implements an isometry between L2 of the physical space and L2 of phase space. So here it is as an isomorphism. Of course, you can make it an isometry by appropriately normalizing your cutoffs. One thing you should notice is that we're only using the wave packet refinement of the Littlewood-Paley decomposition when sigma is small. When we deal with large values of sigma, then we purely use a Littlewood-Paley decomposition because that's good enough for our analysis. The refinement is important asymptotically. It's important when we deal with large momentum, which is to say we deal with small values of sigma. Now, in a few minutes, I will show you how we use this L2 isometry and construct an LP theory based on it using Hardy-Space methods. But before I go there, I want to point out the key technical idea and the proof that fundamentally exploit the nature of this decomposition. So let's have a look at these two operators. We have a wave propagator here and we have a transport here. These are Fourier multipliers respectively with symbol exponential I length of psi and exponential I omega dot psi. if you want to discuss the LP mapping properties of these operators using your favorite Fourier multiplier theorem or spectral multiplier theorem of Fermat type, you won't be getting very far at all. In fact, you won't even be able to prove that this transport is LP bounded, which is really silly because it obviously is. It is just a translation operator. Now, going beyond that, you certainly won't be able to discuss the optimal Sobolev space mapping property of the wave propagator in that way. However, and that's where the miracle is, when you look at the difference between the two and you restrict your attention to the support of a wave packet, then a Fourier multiplier will be able to describe quite properly the LP mapping properties of this operator. So if you restrict that to the support of a wave packet, and let me remind you that this support is such that if this is non-zero, then omega dot xi is roughly 1 upon sigma, and nu dot xi is smaller than 1 upon square root of sigma when nu is orthogonal to omega. Let's have a look at the Fourier multipliers with these symbols, and let's try to prove that they are LP bounded uniformly in sigma and omega. So maybe just to simplify, let's take omega equal E1 for now. It all works the same for other directions. And if I take psi1 and I differentiate m sigma omega in that direction, and I take the supremum over all non-zero xi, this is the quantity I need to control to apply my Amanda multiplier theorem. And what I'm going to get from that by a little bit of computation is that what I really need to be able to control is the supremum of xi1 times xi divided by xi1 minus 1 in the region where xi1 is roughly 1 upon sigma and xij is smaller than 1 upon square root of sigma when j is above 1. And now I'll let you do that exercise. You can find that this is uniformly bounded, uniformly in sigma. So this allows you to apply a multiplier theorems and prove uniform boundedness of the Fourier multipliers with this symbol in LP for all p in the reflexive range uniformly in sigma and in omega. And that is a critical aspect of our proof. So asymptotically in the regimes where sigma is very close to 0, once we implement the wave packet transform in an appropriate unconditional LP way, we essentially won't see the difference between a wave propagation and a transport in the direction of the wave packet. This is done here with Fourier multipliers in the simplest case where my operators don't have coefficients, but appropriate functional calculus technique will allow you to move that into the realm of operators that do have non-trivial and in fact rough Lipschitz continuous coefficient. The point really is that the way we prove the boundedness of that in LP is not using any advanced Fourier integral operator theory. It's using basic Fourier multiplier theorem because on the support of the wave packet transform, these two symbols are close enough to each other.
Now, to move to operators with coefficients, I am going to need an appropriate functional calculus, and this functional calculus will come from the transport group, the group generated by the Dirac operator. This is a bounded group on L2, which has what's called finite speed of propagation that comes out of a general theory due to Alan McIntosh and Andrew Morris. But what we need to prove is that this group is actually bounded on LP for all values of P. Now, to do that, you look at the system of ordinary differential equations that defines this transport group, and you try to prove LP estimates. And you realize that really all you have to do is get LP estimates for one-dimensional analog, but not just LP estimates for the one-dimensional transport group, but also LP estimate for the one-dimensional wave group with Lipschitz coefficients. But the good news is one dimension is that the transport group is actually similar up to a bi-Lipschitz change of variable to the standard translation group, which also makes the corresponding wave group similar up to a change of variables to the one-dimensional standard wave group, which we know is bounded on LP. And so you lift the boundedness on LP of these one-dimensional objects to a boundedness on LP of the entire transport group. Now, it's worth pointing out that this bi-Lipschitz change of variable technique only works in one dimension. If I consider this full Dirac group here and I assume that it can be obtained from the standard transport groups through a change of variable like that, I will derive the contradiction on the constraints that my change variable will need to satisfy. So there really is a big difference between this Dirac operator and this kind of Dirac operators. Nevertheless, I can get the LP boundedness of the full Dirac groups from its one-dimensional counterparts fundamentally because it can be written as a product of the one-dimensional Dirac groups. Now, the same is not true for the wave group. That would be too easy. And that's because the wave group cannot be written as a product of one-dimensional analogs. Now, as soon as you have an LP bounded group, you have a Phillips functional calculus for its generator through Kaufmann-Weiss transference principle. That is to say, you can form function of the Dirac operator dA, and you can estimate the norm of this as a bounded linear operator acting on LP just by considering the Fourier multiplier with symbol psi lifted to the Buchner space of LQ functions with values in LP. Now the good news is that in 2021 we have a whole range of UMD valued Fourier multiplier results at our disposal to estimate this type of quantities. So the result I was mentioning earlier about appropriate bounds on the Fourier multipliers will automatically give us bound on these quantities. And we can plug x equal LP. We could also plug x equal these Hardy FIO spaces that I'm going to mention in a minute.
Now I can finally define for you the Hardy-Sobolev spaces that we use in this paper. And to do that, I'm going to see them as subspaces of some kind of 10 spaces, like all the Hardy spaces that came before them. And more in the spirit of this talk, I'm going to think about them as being subspaces of spaces over phase space. And the specific type of square function spaces over phase space that I'm going to use are the so-called LP with value in TP2 spaces. I've given their norms here, and let me briefly run you through that norm to understand what it does. So what we do is, well, with respect to the physical variable, we just take an LP norm. With respect to the angular component of the momentum variable, we average over all directions in an LP way. And then what we do with respect to the scale variable sigma, which remember is 1 upon the radial component of the momentum variable, then on that we do take a L2 norm with respect to the measure d sigma over sigma. So it's a square function norm in that sense. It has an extra twist, which is this averages here. This is the typical 10 space twist, which means that we're not really looking at the function pointwise. We always average the function over balls in the physical space RD at the appropriate scale. So that gives a little extra smoothing of all the objects we look at, and this extra smoothing is just ridiculously useful technically, and it does not turn out to be some kind of cheat because we do get the optimal LP mapping properties from that. So we're going to see our Hardy spaces as subspaces of that, and you can see all sorts of classical Hardy spaces as subspaces of functions of a space of that form. For instance, if you take the most classical real variable Hardy space defined by Pfefferman and Stein back in 1972, the way you see it as a subspace of L1 with value in T12 is by using Fourier multipliers to get Littlewood-Paley pieces of your function, and that gives you a function of the original spatial variable x, the scale variable sigma, and that function is just constant in the angular part of the momentum omega, and that gives an equivalent norm to the classical Hardy space H1. So now, to get our Hardy-Sobolev FIO spaces associated with dA, we have to do two things. First of all, we are not using Fourier multipliers. We're using the Phillips functional calculus of the transport group. So here, all our cutoffs are defined in terms of this functional calculus instead of being defined in terms of Fourier multipliers. Secondly, to get Hardy-Sobolev FIO spaces as opposed to not FIO spaces, we follow the wave packet transform philosophy. So when sigma is large, that is to say when we deal with low values of the radial part of the momentum, then we just use a Littlewood-Paley type decomposition. But when sigma is close to 0, we refine that in the wave packet transform way, so using wave packet transform here, and this is now dependent on omega, and we're going to
average over all those omega. And then that gives you HP FIOA if you want, and if you want HPS FIOA, so you want a regularity parameter S and Hardy-Sobolev spaces as opposed to just Hardy spaces, all you have to do is add some weights to this part that correspond to the interesting values of the scale variable. And that gives you the appropriate scale of spaces. Now the question is, how do I prove everything I need to prove on these spaces? So we need to prove that the transport group is a bounded group on these spaces, and we need to prove that the resolvent of the operator L map these spaces in the right way, so just change the regularity parameter, and we need to show that you can swap the transport group and the wave propagator thanks to a Fourier multiplier argument and the transference property for the transport group. So all of that is based on key properties of the functional calculus of DA that are similar to heat kernel estimates.
So here they are. These are the decay estimates that are critical to all of the arguments in the paper. Now they look very much like heat kernel bounds or standard off-diagonal bounds coming from the parabolic world, except that we're not using the Euclidean distance between the set E and F. We're using an anisotropic distance that is adapted to the direction omega of the wave packets for which we're proving the decay estimates. And this distance on physical space, but in the direction of omega, or preferring the direction of omega, really comes from a metric on co-sphere bundle that captures the contact geometry structure that is so helpful in dealing with wave equations. So what we're having here really is a way of measuring a diffusive behavior, but not really on physical space, but more on co-sphere bundle. That is physical space cross SD-1 to take the directions into account and therefore be able to take into account the cancellations of waves going in orthogonal directions. And this is really the critical idea here. By changing our geometric perspective on what we mean by a off-diagonal estimate, we can bring the techniques from harmonic analysis of parabolic PDE to wave equations.
So this concludes the talk, and I want to leave you with the following take-home message. The harmonic analysis methods that are really good at treating elliptic and parabolic PDEs can also be used to solve wave equations, but what you need to do is think of diffusion not as happening on physical space, but as happening on phase space. And I'm going to stop here. Many thanks for your attention.